represents how spread apart your data is relative to its mean, MEAN, or in other words, its average. So if you have a collection of numerical data, you can calculate its average or its mean, and then when you find the standard deviation, it is a number that represents how spread out in general as a whole the data is around that average value. Okay, so that's it. So let's look at the formula. There are actually two different situations, so two similar but slightly different formulas that can be applied to calculate a standard deviation. Okay, so let's take some time to go over these formulas, just the big picture here, and that way if you're someone that gets lost in all the calculations, maybe you're memorizing steps, this might help clarify what you're actually doing, and hopefully you can trust the math and trust the formulas and build a little confidence with this notation, because right now this might not even look like math to you, just depending on how comfortable you are with this type of notation. But I'm hoping that this can help you develop intuition and what you're actually doing. And so we'll talk about the two different cases here, and if you want an exact example, we will work one out in a little bit. Okay, so first of all, the difference between these two. So this first formula applies for population standard deviation. So if your data, your numerical data, your quantitative data covers an entire population, so if somehow you managed to collect data for a full population, you would use this formula. Now I think more often than not you will actually have sample data, a sample standard deviation. So you would have quantitative data collected for a subset of the full population. In that case, you would use this formula here. Okay, so you would find the standard deviation of a sample of data or a population. Now, sometimes, by the way, you're not asked to calculate this. Sometimes you're just given sigma. That's okay too. But if you ever see sigma and mu like this, sigma and mu, they come paired together usually. You are looking at population statistics, and if you see S and X bar like that, that would indicate that you're looking at a sample. Okay, so mu is the average, it's a population mean. Sigma is your population standard deviation. X bar is a sample mean, so the average of a sample, and S would be your standard deviation. So that's the only subtle difference there with the notation here, because you can see here the pattern looks very similar, right? We have some square roots, we have stuff here, which we'll talk about, the n-1 versus n, but then we have this thing, we have xi's, which is the same for both, but then we have mu and x bar. Okay, so just pick either formula and use the corresponding notation here, okay, depending on population versus sample. So what you're basically going to do is, let's just start with population first. So the first thing you're going to do is find the mean, like we said. So if you have lots of data, you add the numbers together, the results together, and divide by the population. So when you find the average because when you do this here, we're going to have positive numbers, and then this sum, this capital sigma, means that you add them all together. So you find the difference, you square them, and then you add all of those squared differences together, and then you divide by the number of the population. You divide by n, and another way to write divide by n is to multiply by 1 over n, right? That's the same thing. So you take this entire sum and divide it by n, the total population here. That whole thing is called the variance, and then you take the square root of the variance and you get the standard deviation. Okay, so I hope that makes sense, at least formula-wise and notation-wise, and therefore the steps. So find mu, make a table, take each of your sample points, or not, in this case not sample points, data points, subtract the mean so that you do have a difference, square that difference, or all of them, like make a table and square each of those differences, add all of those squares together, divide by the population, take the square root of that whole entire thing. Okay, kind of like a distance formula. Alright, so for the sample standard deviation, it's exactly the same thing, except you use S and X bar. So instead of calculating mu, you are calculating X bar. The same way though, so if you have a sample, you add the data together, divide by the number of data points in that sample to get X bar. Find the difference between each of your sample points and that average. Square each of those differences in your table. Add all of those squared differences together, and now you divide by or multiply by 1 over. It's the same thing. Divide by n minus 1, 1 less than the number of points in your sample. Okay, so this little adjustment here, why do we do this? It is because n minus 1, so that's going to be a little bit smaller, right? This n minus 1. So if you had 20 points, if you divide by a smaller number, so if you divide by 19 instead of 20, this will be a little bit bigger. When you divide by a smaller number here, if it's all positive, which it is, each piece is going to be a little bit bigger, right? So when you take the square root, it'll be a little bigger. So this thing is actually called Bessel's adjustment. Something like that. Bessel's correction or Bessel's adjustment. And the idea is that when you have a little bit bigger for your sample standard deviation, it accounts for the fact that you only have a subset of the population, so you might have more variability in general. Whereas here, if you have the full population, if you have all the data in your population, you don't have to adjust for that, right? Because you literally have the entire population, or data for the full population. Whereas for a sample, if you only have a subset of the population, the rest of the population might have more variability in that data, so you adjust for it by dividing by n minus 1 instead of n. Okay, so in your exercise or your example or your situation, you should be able to tell if you're looking at data for a full population or a sample. So just use this accordingly and then use this part accordingly, but then the rest should all be the same, right? The formulas are basically the same. So let's look at an example. I have one with 1, 2, 3, 4, 5 data points here. I just want to keep the numbers pretty straightforward, and also I think this is enough data points to see the pattern and not too many to where we get bogged down in the numbers. So hopefully this kind of gets us started here. is for a sample, then we will use X bar. But either way, the calculation will be the same here. We do 4 plus 8 plus 6 plus 5 plus 3 divided by the number of numbers, right? So 1, 2, 3, 4, 5. So that would be 4 plus 8 is 12. 12 plus 6 is 18. 18 plus 5 is 23. 23 plus 3 is 26. 26 divided by 5 equals 5.2. Okay, so that means that the average of this data is 5.2. So you'll either write mu equals 5.2 or x bar equals 5.2. I would say most likely you're working with an x bar here because we only have 5 data points, but who knows, maybe we are somewhere with the population of 5. So that would be mu and x bar. So then the next thing would be to make a table, right? For each of these steps, we're going to take each of our data points and subtract by this average. So what I'm going to do here is I'm going to make one table for the two cases, but you can just pick whichever notation suits your situation. So, because we're kind of working it out for both right now, that's okay. So first you'll have xi. So basically x1 is 4, okay, and then I'll assume you understand the idea. X2 would be 8, x3 is 6, x4 is 5, and x5 is 3. So let me actually go ahead and make this a little more clear here. So this is xi. Alright, okay, so xi, and then the next one is going to be xi minus the average, right? So xi minus mu, or, and so you'll just pick whichever situation applies. So xi minus mu or xi minus x bar. Okay, so either way, that's just like which row to label. So if you were to do this on, for instance, an AP statistics test, you would want to pick which one applies here. So not both, you would just do mu or x bar. But you do 4 minus, and we know that the average is 5.2 for both cases, so like this, 8 minus 5.2, so this is our difference. Okay, 5 minus 5.2, 3 minus 5.2. So you go ahead and plug this all in, so 4 minus 5.2. And of course, if you have like a program or you're comfortable with all that, you can definitely do shortcuts here, but I'm just going to do this just to make it very clear. So 2.8, 6 minus 5.2, 6 minus 5.2 is 0.8, negative 0.2, and 5.3 minus 5.2 is negative 2.2. Okay, so we just found the differences. Then the next step is to square because if you get a negative number, you know something went wrong here. As I was saying earlier, so 7.84, 0.8 squared is 0.64, 0.2 squared should be 0.04, 2.2 squared is 4.84. Okay? So we'll do a little good check after this to kind of see if our answer makes sense. So for right now, we're just gonna trust the math and trust the calculations here. So this is the square of all of the differences. So that's what we did this part. So now we add them together. So just trusting this step by step, we go ahead and take all of these and add. So we add them all together. 1.44 plus 7.84 plus 0.64 plus 0.04 plus 4.84 is 14.8. Okay, so the sum is 14.8, and it's the same for both of them, like we said, with the slight notation difference. The formula part is still the same. So now this is where we go from population and sample. This is the difference where we divide by n versus n minus 1. So for the population, if we're treating this whole thing as though it's a population, so we'll just say n equals 5, then we take this number. So we'll just go ahead and like finish the whole question actually. So we'll say that sigma equals the square root of 1 over 5, which is the same thing as dividing by 5, times, and then our total was 14.8. So this is the square root of whatever 14.8 divided by 5 is, 2.96. So the square root of 2.96, which is approximately 1.72. Okay, so our standard deviation is about 1.72 if we had this as the population. If we have it as a sample, the same data but as a sample of 5, then we would have n is 5, but then we do n minus, but then we use n minus 1 is 4. So then we would say s equals the square root of 1 over 4 times 14.8. So 14.8 divided by 4 is 3.7. So this would be the square root of 3.7, which is approximately 1.923, but I'll just say 1.92. Okay, so as expected, our sample standard deviation is a little bit bigger than our population one, because we have this adjusted number, this Bessel's correction, because we only have a sample, a subset of the full population. So there might be a little bit more variability in the other data. So we want to account for that. So that's why this is a little bit bigger. So if we had a population of 5, we'd have this sigma of 1.72. If we have a sample of 5, then we have this S equals 1.92. I hope that makes sense here. And that's about it. So of course, oftentimes you'll have more data points. You might have to program this step. You would just do xi and then xi minus mu or x bar, and then the thing is, once you calculate the mean, you just take each of those xi's and subtract the mean. Then you take those differences and square each of them, then add those squares together. Okay, so the last thing I would say to do is to just do a little gut check here. So we got 1.72 and 1.92. Both this is the furthest one away and this is the furthest one away from 5.2, it kind of makes sense, right? To kind of average this out. It's like a weighted distance formula, right? So in other words, I guess it makes more sense to kind of just make sure you don't have a crazy outlier. Like if you got 10 for the standard deviation, that wouldn't make sense because, you know, there's not even a number that is 10 away from 5.2 in the first place. We don't have a 15 or a 20 or something like that, right? So just a little gut check would make sense. So I would say that if you happen to be working on exercises and going through this and you seem to consistently get the wrong answer, maybe multiple choice question or maybe just a free response or something like that, if you are often kind of close but not quite, I would say the first thing is make sure that you're remembering to do -1 if necessary, if you have a sample, because that's a thing if you're close but not quite, just applying which formula. Secondly, I would say just make sure that all of your squared number parts are 0 or positive. It should never be negative, because that would make this a little bit smaller if you just happen to accidentally type into a calculator, because if you do like -1.2 squared like this, you will get -1.44 instead of positive. So either put the parentheses or just know up front that these should all be positive or 0. That could affect your answer. Then of course make sure that you're finding the mean in the first place. Make sure that